Okay, let's start the lecture. So today, last time we finished studying the properties of convolution. So about convolution, you need to know the definition, you need to know all the properties, and then you need to know what I'm going to teach now, which is how to compute it graphically. So the technique, so let's say suppose you plot z of n equals x of n convolved with y of n, where x of n is let's say the usual sequence so we take x of n like that, and y of n, let's see, how can I take y of n? Let's pick an easy one. One, like that. All right. So we know that for each n, z of n is sum of x of k, y of n minus k. But it will be convenient to use the time reversal of y. So remember, y tilde of n is y of minus n. So I wish to write y tilde of something equals y of n minus k. What should I put here? Are you sure? Are you sure? No, you're not sure. Are you sure? I was waiting for that. I know you are scared. Because this is y of minus k minus n. So I can rewrite z of n All right? So you wonder why I'm doing this. So that will be clear. That will be clear after I rename my index. I'm going to rename my index as K. Am I allowed to do that? Yeah. You are allowed to call your index anything, provided that you are consistent between this and that. Should be the same letter. It doesn't matter. It's a dummy variable. And let me do the same thing for y. I'm calling the index K. So the reason I call them K is because in this operation you can see K is the variable. Meanwhile, n, you see I said each, right? Each. That means you want to calculate z of n for each n, for any given n. So n is fixed. N is fixed, but k is a variable you have to vary from minus infinity to plus infinity. So it's nice to look at these two sequences as sequences of k. But n, being a given number, looks like a shift here, right? Here you cannot look at this as a shift of k, but here it's a shift of k. But I mean, the advantage of doing this is immediate when you want to calculate z of 0. So to get z of 0, you just need to plot x and the time reversal of y of k. So the time reversal of y of k is, yeah, my example is not so good because after time reversal we don't see its time reversal, but you know what is. So what do you find? Z of 0, you have to multiply these numbers and then add them up. All right? So when k is okay. $5. You know, it's like nowadays, you know, you earn money in any ways, right? You post videos on YouTube, you earn money, things like that. Except for this class, it's free. All right, so how much do you find? So when k is less than minus 3, you only get 0, right? So at k equals minus 2, you multiply this with this. So you get 1. But you have to add with the next one. This plus this times this. Plus this times this. So you get I should go back to kindergarten. Do I pass? All right, so you get z of 0 right away. You get z of 0 right away, so what do? You plot it right away. So okay, here I'm going to represent z of n. I want to keep the letter n. I want to keep the letter n because this is the letter I'm using here, right? And then, okay, let's align. 0 is here, so at 0 you find 9. No. And you know what? You get partial credit. Isn't that nice? But you want to get z of 1. So, sorry, you get what? So you get sum x of k y tilde of k minus 1. So you get this from here, right? So you need to plot the shifted version of this by 1, which is very easy. And what do you find? You find 3 plus 2 plus 1, 6. So at 1 you find 6. Now should I? I'm not, I'm not going to write. You know that z of 2 is going to be the same thing, but you shift y tilde by 2. I'm not going to plot it. You can see it. You can see by yourself, right? When you shift this by 2, so this is shifting this by 1. So you are going to get 1, 1, 1, 1, 1, 1. So you're going to get 2 plus 1. Z of 3 is going to be 1, z of 4, 0. But all of them are going to be 0 starting from 4. So you get this. But you only get half of the points because you still need to, hey, what did I do? You still want to plot the values of z of n for n negative, right? So in this case, the formula is going to give you this plus 1. But again, I'm not going to draw the picture. You shift this by 1 to the left. So you're going to find 4 plus 3 only. Oh, I forgot the 1. Oops. And 0 minus 1 is going to be 4 plus 3, 7. 0 minus 2, you shift again, you find 4. 0 minus 3, you find 0. Seven, 4. So basically, you have to remember that the way to go is to change the name of the index, plot y of k, x of k, then flip y of k, then calculate this operation. We call this operation inner product or dot product. Dot product is a term you know. It's like for vector dot product. It's similar to vector dot product. Do you agree? So okay, so I will say dot product. You need to calculate the dot product between x of k and y tilde of k. And that gives you right away the value of z at 0. At 0. Then to get the value of z at 1, you do the same thing, but you have to shift y tilde by 1 to the right before you take the dot product. Then for z of 2, you need to shift y tilde by 2 before you take the dot product, etc. And for k negative, you need to shift y tilde of k by, to the left. And that gives you the result. Now, I said you need to change the name n into k. You don't have to, because you can, it's basically in your mind. And then you plot y tilde of n, and you don't even need to plot the shifted versions. You should be able to see graphically, do the shift graphically, and then do the dot products graphically. And then when you are super good, you don't even need to plot y tilde of k. You do the flip in your mind, and then you take the inner product. And when you are super good, then I show you two sequences, and then you look at them and you say, it's going to be 9, 7, 4, 1, 0, 0. Like that. Soon, you'll be able to do that. All right? You don't need to, so when I ask for graphical computation, you don't need to write anything. You can show me the plot right away. This is the only exercise where I don't want to see explanations. Any other exercise, I want to see explanations. But for graphical computation and convolution, you are allowed to show nothing and do everything graphically and directly. The reason I say that is that you can write something, but here it will be a question of time. You want to show you can go fast because you want to have enough time to solve the other questions. All right, so here, this is the end of my section about convolution. So now we can proceed to the next section. So convolution was section what? It was section 5, 6, so section 7. Sorry, I need to review my Roman numbers. Building LTI systems. You're going to say, at last, we talk about building, right? We are engineers, right? We are not mathematicians. Until now, you may complain, oh, this is too much mathematics. Is that what you feel? Yes? No? Or maybe it's a new type of mathematics, maybe. You don't recognize the mathematics that you are used to. But let's put it this way. Until now, it looks like only analysis. But now is the time to play the role of engineers, all right? This is the name of the school, right? So I have to pretend I'm teaching engineering, right? At least. So it's about building, right? Engineers are about building. They're not about writing mathematics. So, but before we build them, we need to do some more mathematics. Sorry. But that's the goal, all right? So for those who are getting impatient that they don't see engineering, just wait a little bit. First, we need to do a review. What was the miracle input theorem? What did it say? Something is missing. Yes, you forgot to say LTI, because without LTI, you see, without LTI, we know it does not work. You see, very important. So, if S is LTI and G of N is its impulse response, therefore G of N by definition is S of delta of N. Then for all inputs X of N, S of X of N, we can predict it, but we also have the formula. Initially, we wrote it as sum of X of N, G of N, sum of X of K. But that was symbolized by convolution. In fact, using commutativity, we like to write in this order. All right, so that's the first theorem. This is the first theorem. I think in my country we do this to say first. Here you say this, right? No? Depends on the country. This is the first theorem that we learned in this class. But amazingly, after 2 weeks, you will forget about it, because when I will ask you again, you will have forgotten it. The problem is that now we are going to have a second theorem, which is going to make you confused. Temporarily, we don't know anything about the LTI systems. We only know about convolution, all right? So, we are going to have a convention. Let f of n be any given sequence. then this. So I'm going to show a system but what I'm going to write inside, so this is a system, okay? But what I'm going to write inside is the name of the sequence f of n. And this symbolize the system S, the system such that y of n is equal to f of n convolved with x of n. It's symbolized. All right, so this can always be defined because this definition is well defined. F of n is given. The convolution operation is known. So this gives you a formula. So this gives you a system. You can always make that system no matter what. So now the theorem, it says, I'm going to call it theorem 2. It says the following. There are two parts. Part 1, this system is automatically LTI. And second part, its impulse response is automatically equal to f of n. Now a theorem, again, it's not something I tell you because it's something I like. No, it's because it's something that is true regardless of me. So let me prove it. One. So one, we are going to prove linearity using the two tests. Remember that there's just to be more detailed. All right. So first, prove test 1. So what we are going to do, you know, the usual thing. We are going to so you remember you basically need to input 2 inputs, you get 2 outputs. Now, and then you take I'm sorry, here I'm already trying to prove linearity, but let's start with time invariance first. All right, so let's start prove time invariance. So we want to take S prime as the shifted version of X. And then you want to see what is Y prime, okay? Compared to Y. Then what is Y prime? Now we are going to use the definition of the system. We know by definition it maps Y of n into the convolution between f and x. Here, same thing with x prime. So what do we say? We say that this is going to be clearly all right? But y of n is equal to this. All right? Y of n is equal to this. So when you see this, what do you conclude? Yeah, because how do you get Y of n shifted by a naught? Yeah, there's a name. There's a name. There's a property of this time shift 2. Because of time shift 2, you see this proof is actually an exercise to make you use the properties of convolution. Do you remember that Y of n minus a naught has also another expression? Hey, you are sleeping. Y of n is the convolution between this and this. Y of n minus a naught gives you this expression, but it has also another expression. Yes, you can also get Y of n minus a naught by shifting f. Remember? Now the shift of interest here is the one that shifts x, all right? But what do you conclude? It's time invariant, okay? System is time invariant. But now you want to prove linearity, so prove. Yes?
When we find y of n minus n naught, why are we not shifting both f of n and x of n?
You forgot the previous lecture. You have your notes? Look at time shift 2 property. Yes? Okay, so now we prove You know, there was a professor who gave a pop quiz to make sure that students come to class with the knowledge of the previous lecture. You make me feel like giving you pop quiz. Yes? No? We vote? The advantage is that if I give pop quiz, then the exams they will count less, which is good, no? No? All right. So for linearity test 1, it's similar to time invariance, except that we don't do shifts, but scaling. So if I take x prime equals alpha x of n, then you get this. And then, is there any property you feel like using? The third property was called homogeneity. Homogeneous. Because convolution is homogeneous, you can put the alpha outside. But that gives you what? That gives you y of n. So, is it working? Yes. Test 1. Test 1. Okay. Test 2. So, what do? We take three inputs. And then the third one, we take it the sum of the first two. So then y prime is going to be the convolution between f and this, right? And what property do you feel like using? Right. So this is equal to, because convolution is distributive, then you get this plus this but that, what do you recognize? So test 2 works. So it's linear, so the system is linear and time invariant. But that is property 1. Property 2 says that, talks about the impulse response. All right? So what is the impulse response? It's the response of S to delta of N. So the impulse response is the response of the system to delta. So the impulse response is here. But by definition of the system, it is what? F of n convolved with delta. And what do you say now? Why? Neutral element. Neutral element. So the impulse response is equal to f of n. Done. You see, until now, or before, what we saw is that if you assume that the system is LTI, then it has a number of properties. Here we have no more LTI systems. We make a system by ourselves. You see, I choose the sequence H of n, and I make this system. I make it myself, such that the input is transformed into its convolution with f of n. But the theorem says that if you do that, you automatically make an LTI system. So with the two theorems, theorem 1 and theorem 2, we know that we can make all possible LTI systems existing on Earth in this way. And to emphasize this, I'm going to ask you a question that students, they have a hard time answering. I will call that fundamental experiment. Start with a given system S that is known to be LTI. In fact, I'm going to make that as 3 steps. Okay, so step 1, start with a given system S that is known to be LTI. Step 2, measure its impulse response and call it H of n. And third step, make the system make this system. So, right? So, I repeat, You start with a system that is known to be RTI. I call it the system S. Measure the impulse response of the system S and call it H of n. You get a sequence. So forget about system S, take that sequence H of n, and then from this sequence, make the system by yourself. Question? Is there any relation? Is there any relation between S and this? You cannot answer? I'm waiting. You say something. Yes? Can you give me the final answer?
Yes.
All right. So can you give me that relation? No. Here you gave me the relation between S. No. Because I'm not asking the relation between S and H of n. I'm asking the relation between the system S and that system. I'm asking the relation between two systems. Remember, this is not a sequence, this is a system, all right? It's a system on which you have written the name of the sequence, but it's a system. Yes?
We wouldn't be able to know this relation. We only know what our new system does.
All right, I give you the answer. All right, so to your answer, here's my answer. Haha. It's so obvious that I'm going to give you two proofs. Normally one proof is enough, right? I'm going to give you two proofs. What do we know from the miracle input theorem? You see, I said you are going to forget the miracle input theorem within 2 weeks. Yeah, it's within 2 weeks, like within half an hour. What does it say? It says that once you know the impulse response of S, you know the system completely, right? But it says more than that. We even have the explicit formula of S. And what is it? Yes, some blah, 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 which is also right? I mean, that's the miracle input. You don't like my religion? you don't want to follow me? This is the thing that says everything, all right? You just know the impulse response, so here it's H of n. So you can predict the response of S to any input, but we can predict, but not only that, we had the formula which is the convolution. Okay, so we know that, right? Meanwhile, how is this, the second system, how is it defined? We just defined it here. All right, we defined it here. This symbolizes the system that transforms y or x into its convolution. Right? This is it was defined like 5 minutes ago. So this by definition is such that y of n equals h of n convolved with x of n. Right? So the two systems are equal. Do you agree? So the two systems are equal. Because they give the same formula. It was so obvious that you couldn't see it, because you know how I define this? I define this actually by copying the formula of the LTI system. I just copied, but you didn't realize. I'm going to give you a second proof. I know every semester when I teach it, I can see students, they cannot answer. Is it because it's too abstract? Yes, it's too abstract. That's why. But it's logical. And I think students, they say that, they tell me that they don't have enough logical training. I mean, if you don't agree, then tell me why you find this difficult. All right, proof 2. S is LTI. Why? Because we are told so. Because of assumption. Right? And its impulse response is h of n. Why? Because it was the assumption. All right, so you agree with this? Now this system is LTI. Why? Theorem 2, yes. Not by assumption. I heard somebody said by assumption. No, it's by theorem. Remember, definition and theorem is different. The assumption, definition is something you decide. Theorem is not from you. It's from outside. Because by theorem 2, property 1. its impulse response is h of n. Why? Why? Yes. You know, I was ready to shoot at what answer? If you say by assumption. By theorem 2, property 2. Now you conclude. What did we say about two LCI systems that have the same impulse response? So they are then equal because they are both LTI systems with the same impulse response. All right, so I on purpose I give you these two proofs because it's like to train your logical reasoning. All right, so now is the time to do engineering. Okay, so maybe for some of you it's going to be really enough of abstract reasoning. We are going to start going into the lab and try to see if we can, from what you learn in logic circuits, if you can make LTI systems. The first one that is of interest is called delay element. So the delay element is a system that is symbolized by this, and it is such that it maps x of n into each shifted version by 1. It's called delay element. First question, with what you learn in EE210, switching systems, can you make such a system with logic circuits? What? How do you make a buffer? Latch? Something, no, this something more basic. No, something less basic. Yes, flip-flop. You remember that? Flip-flop? All right, now, a single flip-flop performs a delay of a sequence of single bits. All right, so you have a sequence of bits. You know, in 210 you learned about combinatorial circuits and sequential circuits, right? That was the second part of the E210, sequential circuits. So in sequential circuits, you can talk about sequence, but you study sequence of bits, right? So, but a number, basically, it's like in a computer, a number is like 32-bit number, all right? So it's like 32 sequences in parallel. So with 32 flip-flops, you make a delay element of 32-bit numbers. All right, this is electronic side. System side, we don't know anything about gates, circuits, hardware. We just are interested in math. The question is this an LTI system? Yes. Yeah, this is the simplest one. You know, if you cannot say yes to this, then you're in trouble. I'm not going to go through the proofs. This is obviously. Okay, I don't use that word at an exam, right? Because I see students who I say I say justify, you know, they say, oh, it's obvious. You know, sometimes they what I see is like you know, when I give a question of the type show that you get y of n equals this, then I see students they start from the beginning, and then they get stuck, and then they take y of n and they go backwards, and then they steal the gap, and then they write, oh, this is obvious. You know, I'm laughing because it's true. The students, they do that. Maybe some of you recognize themselves. All right. Now is the difficult question, fundamental question. Does there exist a sequence G of n such that this is equal to this? And if so, what is G of n? Can I give you a hint? The answer is above in your notes. Maybe one page before. But you didn't tell me what is H of n. But what is the impulse response? It's H of n. You see? There's no H of n. So the impulse response, okay, what is the impulse response? All right, so what is it explicitly? Yes, you are going to get it. I feel you are going. Yes, say it. I'm going to. No, but you have it, but you are not having it. you have it. Yes. Did you hear what he said? But do you understand why this is the answer? No. Look at these three steps. What does it say? If you follow this procedure, you are guaranteed to find a system like that is equal to S. All right? So can you follow this procedure with this system? So you have to find the impulse response of this system. What is the impulse response of this system? What? Yes? So the answer is yes. Just follow the fundamental, what I call fundamental experiment. It's no longer an experiment. Now it's the truth. Find no. Fundamental experiment is look, the 3 steps I showed you. The time shift 1 does not appear there. Find impulse response of this. No, take. I'm sorry. Take. So with. So yes. With G of n equals impulse response of this. So how do you get the impulse response of this? You get it right? Impulse response is here. But how much is it? It's delta n minus 1, right? So we know that this system and that system are equal if you take G of n to be delta of n minus 1. As a consequence of fundamental experiment. So I can proceed because I know it's true, but I'm going to do as if you still get skeptical. Like, oh, this is too abstract for me. I really don't get it. So I'm going to do a verification. For those of you who are skeptical, I'm going to see whether these two systems are equal. Okay, so I'm going to verify whether this and this and that. All right, so we're going to compare these two. Oh, I'm not able to catch the handle. I don't want this. So we input x of n here and here, and we test whether we get the same thing, all right? So here we get x of n minus 1 by definition. And here, by definition, what do we get? By definition. So we write this first. You obtain this by definition, all right? All right. But what do you feel like writing here? Yeah, so what property gives you this? Time shift 1. So you talked about time shift 1. Yes, now it's coming. But we didn't need to do this verification. I'm doing this for those of you who just couldn't understand the general reasoning. from the general reasoning, we knew already it would be the same thing. Second, okay, so this is one LTI system you can make in the lab. The next one is, oh yeah, I'm going to call that the scalar. Yeah, multiplier if you want, but multiplier. You can call that multiplier. Scalar, I prefer to call scalar, but multiplier. So it's a system that is going to be represented like that. And we put a box. And no, sorry, sorry. Why am I writing the same thing as delay element? So what is going to be? Yes, yes, of course. Okay, so this is even more obviously LTI. All right, so what I'm going to do now, is there any, what's that? It's a wrong, that's funny. Something happened. All right. Answer my question. So what is it? Yes. Yes. So, in fact, you know, you proceed the same way, right? Oops. Sorry, I'm going to do just copy and paste because it's just the same thing. So in fact, what I need to do is so I get the impulse response of this, and you get alpha delta now. Sorry, give me one more minute. I want to do the verification. Sorry, I'm going to do extra time. 1 minute. Let's do verification. So the verification is I'm sorry. So the verification is that you input the same input to these two systems. And all right, so this is, oops, sorry. So on top of it, you obtain alpha x of n. And here you obtain what? Alpha delta of n convolved with x of n. And then what property do you feel like using? What's the name? Homogeneous. You find this. And then what property do you feel like using? The neutral element. And you find alpha x of n. And they are equal. All right? So, all right, we are done. All right. So next Monday there's a surprise. Next Monday you come, there will be nobody. But you can come if you want. Wow. All right.